Hello Vulkan developers! Today we're going to do something fun for a change. Every graphics application needs some kind of a user interface. Whether it's tweaking light properties, manipulating object transformations, or simply changing the window clear color in real time, you need controls, and that means a GUI library. Hopefully one which provides an easy-to-use API with a wide variety of graphics widgets. There are plenty of GUI libraries out there, but when it comes to OpenGL and Vulkan, one stands out above the rest. Dear ImGUI. It's lightweight, fast, flexible, and widely popular in the graphics programming world. It even supports DirectX, so all the major graphics APIs are covered. Today, we'll walk through how to bring Dear ImGUI into your Vulkan application. As I said, ImGUI is very easy to set up and use, but there is just one tiny implementation problem. ImGUI is an immediate mode library, which means the entire UI is rebuilt every frame. In OpenGL, that's no big deal. You're constantly rebinding VAOs, switching shader programs, and juggling draw calls anyway. But Vulkan is just the opposite, and we try to prepare as much as possible upfront and reduce the runtime overhead to the bare minimum. ImGUI breaks that pattern. In Vulkan terms, it means that we will need to record the GUI command buffer on every frame, whereas in our current workflow, we record the command buffer offline, and during runtime, we just update uniform buffers and submit the command buffer for execution. In addition, I want to be able to turn the GUI on and off, so it should be possible during runtime to get rid of its overhead entirely. Here's how we currently handle rendering in Vulkan. For each swap chain image, there is a matching command buffer. When an image is ready, its corresponding command buffer is available. We loop over all the command buffers and begin each one for simultaneous use. We insert an image memory barrier to transition the image layout to color attachment optimal. Then we begin the dynamic render. The pipeline is bound to the command buffer, and the draw commands pertaining to the model to be rendered are recorded. We end the dynamic render, insert another barrier for transitioning to layout present, and finally, we end the command buffer. So this happens only once, and during runtime, we just need to submit the command buffer. For ImGUI, we're going to need another command buffer, which will be recorded on every frame, as long as the GUI is presented. If this command buffer is submitted after the main one, we have a problem since there is already a layout transition for presentation, so the second command buffer cannot execute properly. The solution that I came up with is to create two sets of command buffers, where each set has one command buffer per image, as usual. One set is for the case where the GUI is disabled. This set of command buffers maintains the current behavior. The second set is when the GUI is enabled. In this case, the main command buffer transitions the layout to color attachment optimal, but it doesn't transition it to layout present. It also clears the color and depth buffers as usual. The GUI command buffer assumes that the layout is already color attachment optimal and doesn't clear the color and depth buffers. We record the ImGUI stuff into it and transition the layout for presentation at the end. The two command buffers are submitted together into the queue. In general, Vulkan doesn't guarantee any order in the execution of multiple command buffers that are submitted separately, so they may overlap each other, and this is a problem in our case because we want the GUI to always render last. Such cases require a pipeline barrier or a semaphore. We're going to use the capability of the VKQSubmit function to receive an array of command buffers. In this case, Vulkan guarantees the execution order within a single submit call in the order they're listed. So we are good to go without any other synchronization mechanism. In terms of software design, I consider the ImGUI API to have two parts. First, we have initialization, which we should try to make as generic as possible to fit many projects. Then we have the widgets themselves, which are probably application specific. How you manage the widgets and whether you can apply some code reuse techniques is up to you. Therefore, I created a class called ImGUIRenderer to take care of the setup, while the code that fiddles with the actual widgets is inside the application. Okay, let's start by installing ImGUI. Search for ImGUI and go to their GitHub page. Now, in terms of installation, they kind of do have some sort of a release page with zip files, but this is only for the demos. So anyway, I think that the best way to do it is by simply cloning the repo. Okay, so get the location and clone it to your machine. And as you can see, I already have it right here. So let's take a quick look, okay? We have a few H files and CPP files here at the top level directory. And then there's a folder called Backends, which includes the backend support for each platform that ImGUI can work on, such as DX9, DX10, 11, 12. You can see we have both GLFW and also for the older FreeGLAT, OpenGL 2 and 3, and etc. And here we have Vulkan. So from here we only need Vulkan and GLFW. I'll show you that in a second. In addition, we have some documentation and lots of examples. So basically most of the code here is not required. So what I did to make it easier for the people who want to work with my sources is the following. In my source tree, under common and third party, I created a directory called ImGUI and then GLFW. And here I copied all the files from the topmost directory, all the source files, except the demo. Okay, you don't need the demo. I copied these guys into this directory. And in addition, from the backend directory, I copied these files. Okay, we have the implementation of GLFW, CPP and H, the same for OpenGL 3, also the loader for OpenGL 3, I guess it was needed, and then Vulkan. Okay, so depending on the type of project that you have, if for example you only want to support Vulkan, then you will need the two GLFW files, assuming that you're working with GLFW, as I do, and also the two Vulkan files. And if you don't support OpenGL, simply get rid of it. Okay, so simply pull in all the backends that you need. And it is very straightforward because most of the backends here have just two files. For example, SDL2, SDL3. Sometimes there is an extra file, for example, this guy, but in general, we have just two per backend. Okay, so one option is to create a directory similar to this one with all the required files. And then you will need to update them if you want to keep up with latest development of ImGUI, or you can work directly with the directory that you cloned and then simply pull in the original files into your project. And then you can do like git pull here and update them, and then they will be updated automatically in your project. Okay, so give some thought into how you want to manage the files. For me, it was easiest to simply copy them here, and when people clone my sources, then they have them automatically. So now let's see how to organize Visual Studio for ImGUI. In my solution, I have a Vulkan folder, which you're probably familiar with by now, and I have the Vulkan core library and source files. And I have my Vulkan specific files here, as well as stuff which is pulled in from other places in my code. So for example, common OGL dev, these are files which are common to Vulkan and OpenGL. So what I did is to create a new folder here called ImGUI, and I pulled in the 6 files that we need. So we have 4 files that are kind of like the core of ImGUI, imgui.cpp, ImGUI draw, tables, and widgets. These are the base files. And in addition, we have impl GLFW and impl Vulkan, CPP. So if you want to, you can also pull in the H files from this directory, but in terms of building, you just need the CPP files. So this will build ImGUI directly into your project, and you don't need any library, but we do need to access the H files, so we need to make sure that the include path will allow us to access them. Okay, so right-click Vulkan Core, go to Properties, C++, and General, and under Additional Include Directories, you can see that I've added the relative path to ImGUI/glfw. And this is based on the location of the solution directory, so this is probably different in your case. So just make sure to put in the correct path for your workspace. It can also be a full absolute path if you're not planning on distributing your sources to people. As you can see, I have another directory under ImGUI called imguizmo.quat, which also has a folder here with a few files of its own. And this is an optional library, which is not part of the core ImGUI. I cloned it from a different location, and it provides a few additional widgets, which are very useful for 3D applications. So if you want, you can use it as well. But again, this is optional. You don't need it for the core of ImGUI, just this folder. Okay, so these files will provide us with the functionality of ImGUI for every project that works with Vulkan Core. But as I said, since the management of the actual widgets is part of the application code, then we also need to make sure that we can access the headers from the application code. In my case, this is tutorial23.cpp. You can see that I included the ImGUI files here as well. And for this to work, we need to make sure to add the include path to this project. Okay, so this is basically the same thing. We have it right here, and also this guy. And this is it in terms of the installation, so now we can take a look at the code. Let's start with the ImGUIRenderer, and here we have the declaration of the class. So the interface is very simple. We have three main functions here. First, to initialize the object, and this guy takes a pointer to the Vulkan core. Then we have destroy at the end, and prepare command buffer, which will be called in the render loop based on the current image, and returns a command buffer to be submitted. And we'll see later on how this works. In the private section, we keep a pointer to the Vulkan core, also the width and height of the frame buffer, a vector of command buffers, okay, as usual, one command buffer per image, and the handle of a descriptor pool. So this class maintains a descriptor pool for itself. The initialization of the descriptor pool is a bit different than the usual, so I decided to copy the initialization from their example and not use the pool which is in the Vulkan core. But there's no problem in maintaining multiple descriptor pools in your project if it makes sense, like in this case. So let's see how to initialize it. Okay, we get the pointer to the Vulkan core, store it in the private attribute, and use it to get the frame buffer size into these parameters. Next, we create the descriptor pool, and then we initialize the rest of ImGUI. So here's the creation of the descriptor pool. And as I said, this entire code is copied from the ImGUI example. So we have an array here of descriptor pool sizes. Okay, 1,000 elements of each of these types, sampler, combined image sampler, and all the rest. And then we create the pool as usual by calling create descriptor pool on the device that we get from the Vulkan core. The create info defines the maximum number of sets and points into the pool sizes array. Okay, null for the allocator, and we get the handle of the descriptor pool here. So now that the descriptor pool is ready, we can go ahead and initialize ImGUI itself. But first of all, I forgot to mention the include files that we need to put in. So we have to include imgui.h, and this is kind of like a base file which you need whenever you use ImGUI in every project. And in addition, the two specific files for glfw, impl.glfw, and impl.vulkan.h. So of course, this will be different depending on the project. And now in this function, we start by creating a context for ImGUI, and then we call getIO to get some kind of an object of the ImGUI IO type. And as the name suggests, this structure contains a ton of information on the system. So all kinds of config flags and display size and fonts and keyboard and lots of miscellaneous stuff. And you can configure ImGUI in many ways. What I have here is just kind of like the minimum. Okay, first we set two flags into config flags, which are nav enable keyboard and nav enable set mouse position or pause. And these are required in order for ImGUI to interact with your keyboard and mouse. There is also a flag for the gamepad, but since I don't have it here, I skipped it. Next, you set the display size. Okay, the X is our frame buffer width, and the Y is the frame buffer height. And then we have the font scale main. Okay, let's see this one. If we comment this out, click on spacebar to bring up the GUI, you can see that the font is pretty small. Okay, this is the default font size in ImGUI. And if you want to change it, then you need to access get style in the ImGUI namespace and then set the font scale main. So for example, in this case it is 1.5. Okay, I think it looks better. So you can put your personal preference here or even allow the user to configure it. You can also put in a value less than 1, which is almost unreadable, but as you can see, it works. Let's put 1.5 again. And then you can configure the color theme, which I use dark. And let's see how light looks like. Okay, so I prefer the other one, the dark. So these are just very few options for setting up ImGUI in terms of the visuals. And you can take a look at the examples and see what else you can do with it. The next step is to initialize it for our backend. So we need to call a function called ImGUI impl-glfw init for Vulkan. This function takes a handle to the glfw window and a boolean flag that tells it whether to install the callbacks for glfw, to make the keyboard and the mouse work. So we take the handle of the window from the Vulkan core, and install glfw callbacks is of course true. Next, we need to call impl vulkan init and provide it with a pointer to this big structure right here. And there's a lot of Vulkan specific stuff here, which we can provide it from the Vulkan core. So for example, the API version is actually the instance version, which we have in our Vulkan core. Remember that we enumerated it into these private attributes. So now we can call vk-make API version and encode it into a unsigned 32-bit integer and return it. So we have the API version. We need the instance. So we provide the instance handle from the Vulkan core, the physical device, the logical device, the queue family, the queue itself. For the descriptor pool, we will use the descriptor pool that we've created, of course. The render pass is set to null because I assume that we are currently working with dynamic rendering. So if you plan to support machines without dynamic rendering, then you'll need to put in a valid handle of a render pass here. Next, we have the minimum image count. From the physical device, we get the surface caps and the min image count, and also the actual number of images. We have that. MSAA samples, I used 1 bit. I didn't use the pipeline cache, maybe in the future. The subpass is not really used. Set it to 0 anyway, because this is part of the render pass. And set use dynamic rendering to true. Okay, this is important, right? Next, we have the pipeline rendering create info, which I think is related to dynamic rendering. So we set the number of color attachment, which I assume it is 1, and the pointer to the color formats, which we also get from the Vulkan core, the swap chain format, the depth attachment from the Vulkan core, and right now we don't use the stencil, so undefined. And finally, null for the allocator, as usual, and you also need to put in a pointer to a check vk result function. Okay, so this guy is a pointer, as you can see here, it is a pointer to a function which returns void and gets a vk result here, an error code basically. As you can see, it skips the cases when the error is 0. So this is actually called whenever ImGUI calls a Vulkan function, not just errors. And this is very useful for debugging, also performance debugging. If you want to track what ImGUI is doing with Vulkan, then you can use this function to log all the Vulkan API calls. If there is an error, then we print it and we exit, or abort in this case. Okay, so now that the structure is complete, we call impl vulkan init with the pointer to the structure, And in terms of ImGUI, it is now ready for action, but we still need to do a couple more things. First of all, we resize the vector of command buffers. Remember that we saw this guy? We resize it for the number of images. Same thing that we did on the application side. One command buffer per image. And then we create the command buffers using the Vulkan core, same number of command buffers, and a pointer to the start of this vector. So now the command buffers are ready, and we can start actually using the ImGUI library. So we have two more functions in this class. Destroy is very simple, simply reverses everything that we've allocated, the command buffer, the descriptor pool, and for ImGUI, you need to call these three functions. Shut down Vulkan, shut down GLFW, and finally, destroy the context. And finally, we have the prepare command buffer function, which takes the index to the image and returns the command buffer. And remember that this must be called after the ImGUI was created on the application side. Okay, the application contains a lot of ImGUI functions, such as new frame, begin, text, and all kinds of widgets, which must be executed for every frame. So prepare command buffer must be called only after this entire process has been completed. So we start by calling begin command buffer. This is a wrapper for the actual API. Takes a handle of the command buffer, so we use the image index to access the correct one, and some flags. In this case, we use the one-time submit, which means that whenever the begin command buffer is called, the command buffer will be reset. And this is useful for us because we're constructing the UI every time. Next, we call begin dynamic rendering on the Vulkan core. So this function should be familiar to you from 2 tutorials back, from tutorial 21 on dynamic rendering. Back then, this entire code was part of the application class, but since now we need it also for ImGUI, I decided to move it to the Vulkan core, which makes sense in general because I'm trying to get rid of all the Vulkan specific code on the application side. And the only thing that I did is to make it a bit more generic. Okay, so the function takes a handle to the command buffer and to the image index, and a pointer to the clear color and the depth value. So previously the assumption was that we're always clearing the color and depth buffers, but this is no longer true because now we're clearing them only in the main command buffers and not in the ImGUI one. So as you can see, in the ImGUI side, we provide the handle of the command buffer and the index image and null for the two values. And here, when we prepare the color attachment, we check the clear color, and if it's not a null, then we set the load up to be load up clear. And in the case of a null, we set it to load up load, which is what will happen in the ImGUI case. And in addition to that, if a clear color was provided, then we also need to set the clear value in the same structure. Okay, so we dereference the pointer, which is okay because we checked it here. If this is a null, then the system will ignore this attribute and you don't need to touch it. And the same thing for the depth attachment. The load up is set according to the depth value, load up clear or load up load, and set the clear value in the same way. The rest of the function is exactly the same, the rendering info and calling begin rendering. So now that the dynamic renderer is started, we can record the actual Vulkan commands into the command buffer for ImGUI. This is something that ImGUI will do entirely in this function, ImGUI impl Vulkan render draw data. First, we need to get a pointer to the draw data from ImGUI, like that. And then we call this function, we provide a pointer to the draw data and the command buffer to use. And ImGUI will take care of all the rest. After that, we can end the dynamic render and insert an image memory barrier for transitioning from color attachment optimal to layout present. So this was actually the closing image barrier that we used to have on the application side, and you'll see that we don't do that anymore when ImGUI is enabled. Finally, we end the command buffer and we return it to the caller. So this is it in terms of this class. Now let's see how to integrate it into the application code. In our application code, we start by including the same three files, the ImGUI header files here. And I also have this ImGUI ZMO quad thingy, which is optional, of course. Also notice this macro, which is defined before the ImGUI headers, ImGUI define math operators. If we remove it and try to build, we're getting an error from ImGUI that we need to define this macro before including imgui.h. So I'm not entirely sure if this is the correct way to work, or this is just a workaround based on this comment here, and I'll check it later and let you know. But this is how it works right now. So let's bring it back. In addition, I also included the new header for the ImGUIRenderer class. So now let's jump to the private section of the application class. And there are a few changes here. First of all, we have another set of command buffers. Okay, previously we just had a single vector of command buffers, and now we have two. Okay, first of all, when the GUI is enabled and when it is disabled. And we will prepare each vector separately, as you shall see. Next, we have the ImGUIRenderer itself. There's also a Boolean flag for showing ImGUI and a few attributes which will be manipulated by the GUI. This, of course, is highly application specific. It will change from project to project. So now let's jump back to the init function. As you can see at the end, we initialize the ImGUIRenderer and we provide the address of the Vulkan core. Next, let's take a look at how the command buffers are recorded. First of all, we have two sets now, so we need to resize each vector separately, right? With GUI and without GUI for the same number of command buffers, of course, based on the number of images. And of course, we also create the command buffers themselves using the Vulkan core. Same as what we just saw on the ImGUIRenderer. Now let's see how to record the command buffers. So previously there was simply a function called record command buffers, which created the descriptor sets and then did all the initialization, all the recording of the command buffer or buffers. But now, since we have two sets, I factored out the command buffer stuff to its own function, record command buffers internal, which takes two parameters. First of all, we have a Boolean flag for whether we want to include a second barrier, and then the vector of command buffers to record. Now, in the case of the command buffers without the GUI, this is kind of like the default or the usual one, we want to include the second barrier. Okay, this is the regular behavior. So we set it to true, but when the GUI is enabled, we want to set it to false because the second barrier is coming, as we saw, from the ImGUIRenderer stuff. And then the rest of this function is the same, except that we check for the Boolean flag, and only when it is true, we actually insert the second barrier. Okay, so for the main command buffers, we always insert the first barrier to transition from undefined to color attachment optimal. And you can see that we don't do that in the ImGUI. We simply start the dynamic render and do the ImGUI stuff. And here we insert the second barrier depending on the Boolean flag. So now let's jump to the main render function and see how to use these command buffers. So we acquire the next image as usual and update the uniform buffers also as usual. And then we check the Boolean flag show GUI. If this is false, then we simply submit the without GUI command buffer into the queue. But if the GUI is enabled, then we call update GUI, which will do all the ImGUI stuff for adding the widgets and constructing the UI frame. And only after that, we can call prepare command buffer on the ImGUIRenderer based on the image index that we have from here. And we get an ImGUI command buffer back. And now we can create an array of two elements, an array of command buffers. First of all, the main command buffer with the GUI, and then the GUI itself, the command buffer of the GUI itself. And we submit them together into the queue. So as you can see, we have, I think this is a new version which I've added for this tutorial, but I can't remember now. We have two versions of the submit async function. The one that actually does the work takes a pointer to command buffers and the number of command buffers. And then we have a wrapper for sending just one command buffer, which calls the main one like that. okay, the address of the parameter, and 1. And when we actually call vkqSubmit, we set the pointer here and the number of command buffers here, and we can now support submitting multiple command buffers. And since we're submitting them together, they will be executed in the implicit order inside the array. Back to the application code, you can see that we control the Boolean flag for showing the GUI based on spacebar. Okay, just my own preference. But one thing which is very important is the callback to the mouse button. This is of course the callback from GLFW when you click a mouse button. And previously, we would simply forward it to the camera. But now we have a check here for whether the mouse is controlled by ImGui. And only if this is false, then the event or the function call will be forwarded to the camera. So let's see what happens if I remove this check. Go back a bit, bring up the GUI, and now when we touch the GUI, the camera also moves. Because this is how the camera behaves in my code. You have to click the left mouse button in order to control it. But when we touch the GUI, we don't want to affect the actual scene or the main camera, right? So this is a very simple wrapper function defined in the same source file as the ImGUIRenderer. Notice that it is outside of the OGLDevVK namespace because really it has nothing to do with Vulkan. What this function does is to get the ImGUI IO and return the Boolean flag won't capture mouse. And this will be true when the GUI is enabled and false when it is not. And this way we can separate the GUI from the main camera. And now all we have left is to see how the UI is constructed. By the way, we can see here the new begin rendering function, which is now just a wrapper for calling begin dynamic rendering on the Vulkan core. Okay, so when the ImGUIRenderer calls this function, it passes null here for the clear color and the depth value, but the main application code passes in the actual values that we want. So now we can take a look at update GUI, and this is how it works. First get the IO, same as before, and then call ImGUI-impl Vulkan new frame, and ImGUI-impl GLFW new frame, and then ImGUI new frame. Because what we're doing is basically start a new frame, a new UI frame. So we have to do it on all the three levels, Vulkan, GLFW, and then ImGUI. So this is actually not a tutorial on ImGUI itself, it's more about the integration of it into Vulkan, into a Vulkan application. So I'll just show you a bit of what I did, and then you should definitely check the extensive examples that ImGUI provides. Okay, so we have two calls to ImGUI begin, here, hello world, and then here, transform. And what it does is to create two ImGUI windows. Okay, hello world here and transform. And then all the ImGUI functions that come after a begin call will be part of this ImGUI window. Okay, so the first one has some text, and then we have a float slider that goes between 0 and 1, and we get the result here. And we also have a color edit, which goes into this private attribute, which is a GLM vec3. And you can see how this widget works. You can change the color here and see the effect over here. As you can see, this actually doesn't change the actual clear color because remember that we already recorded the command buffers and the clear color there was set to white. So if you want to change the clear color, I think you'll need to record another command buffer. Next, we have the transform window, which allows us to control the position, rotation, and scale. And this one is actually tied to the uniform buffers. So we have a drag float 3 here for the position, and another one for the rotation, and a single float for scaling. And what I did is when updating the uniform buffers, I created a matrix, a translation matrix, based on the position, a scaling matrix based on the scale, and rotations around the 3 axes, and combined them together into a single rotation matrix. And then the WVP is created by multiplying the scale by the rotation, translation, and finally the view projection. So now we can change the position of the object from the GUI, okay, on the 3 axes, also the rotation around the X, around the Y, and around the Z. In addition, you can see that we have these cool widgets here, which are currently not tied to the object itself. So just see how it works. We have the 3-axis widgets and this arrow here, which is good for lighting. So this comes from the ImGUI ZMO library. And this is how you create it, by calling gizmo3d. This is for the 3-axis widgets. And then you get the result in this quaternion right here. So now you just need to translate it into a rotation matrix. GLM provides us with the facilities for that. And the same thing for the direction. This flag, mode direction here, indicates that we want to get an arrow instead of the 3-axis gizmo. After creating all the widgets that you need, remember to have as many end calls for each of your begin calls, and finally call render. So again, after updating the GUI, we can go ahead, prepare the command buffer, and submit it, as we saw. And that's it for today. Let me know what you think of this ImGUI integration and whether you have any idea how to improve it. Thank you for watching, and I will see you next time.